In Unit 7, we're going to focus on area and volume, which are two more applications of the definite integral. We're going to start this week by just looking at the area between two curves, so we're still sticking with just two dimensions. Now, usually when I pose this question, people are able to kind of figure out pretty quickly how we would need to do this. So if you want to find, let's just talk about this visually first. If you want to find the area between those two curves, F and G, F is the one that's kind of bolder and G is the lighter one, then the area that we're trying to find from A to B is this pink area here that is in between the two curves, okay? Well, if I want to find that section, I need to know two things. I need to know the total area underneath F, and then I need to find this area that's underneath G because that's the extra bit that we don't want over here. So it makes sense then that the way we're going to find this volume is to do some subtracting. So the first thing that we want to do is let's kind of talk about this verbally, and then we're going to put it into some calculus here. So the formula, our process is going to look something kind of like this. If I want to find the area between two curves, then what I need to find is the area underneath the top curve, and I need to subtract the area under the bottom curve. This is why if we look at the formal language here with this theorem and what it tells us that we need to do, it says if f and g are continuous on the closed interval from a to b and g of x is defined to be less than or equal to f of x for every x value in that interval. What that's saying is we just need to define a top curve and a bottom curve. So in this case, g of x is the curve that is below every point on f of x. So in this case, f of x is our top curve, g of x is our bottom curve. If that changes, then we would need to subtract a little bit differently. So we know that we use definite integrals to find area. So let's translate this now to the calculus. We know verbally that the area between two curves is the area under the top curve minus the area under the bottom curve. So using what we know about calculus, we will get these integrals represent the area underneath the top curve, the integral from a to b of f of x dx, minus the area under the bottom curve, which is the integral from a to b of g of x dx. And knowing what we know about the properties of definite integrals, we can go ahead and combine these into one, that the area from a to b between the two curves would be the integral from a to b of f of x minus g of x dx. And so that is the rule for how we're going to find the area between two curves. Now, we're going to talk a lot in this unit of this idea of a representative rectangle. So if you think back to when we first started talking about definite integrals, we talked about them in the context of a Riemann sum. And a Riemann sum was taking a whole bunch of little tiny rectangles that we could make between the curves and adding them together. And so the way that that is applying in this case is that we have this rectangle, we need to find the length and the width. Well, the width of our rectangle is going to be delta x, which ends up being the dx part of your integral. And then the height, if I want to know the height of the rectangle from here to here, you can see that that's going to be the y value of f, which is f of x, minus the y value of g, which is whatever g of x is. And so that's how we find the area of that rectangle. So if I want to add up infinitely many rectangles over that span from a to b, that's what we use the definite integral for. All right, so let's look at an example. So for example 1, we want to find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So we need to first get those graphs. So the first one, y equals x squared plus 2, is going to be a parabola that opens up, and it has been shifted up 2 units. So our vertex is going to be here at 0, 2. And then you can plug in some other points, or maybe you know how the pattern works, but we do know it's symmetric. So if I plug in 1 for x, we get 3. And if we plug in 2 for x, we get 6. So we know that our other point is going to be up here somewhere. Okay. Then because of the symmetry, we can go ahead and reflect those points back here. So we know that our graph looks something like this. Okay, then the other graph is a line. Y equals negative x, has a slope of negative 1 and a y-intercept of 0. So it looks like this. My internet is lagging, so this is drawing super slowly today. And then they told us that we want the area from 0 to 1. So the line x equals 0 is right here, and the line x equals 1 is right here. So the region that we want the area of is going to be this one. So that helps us identify, by looking at the graph, that the parabola curve is the top curve and the line is the bottom curve. So that's what we have to know to be able to set this up. So we want to find the integral from 0 to 1, because those are the boundaries that they gave us, of the top curve minus the bottom curve. So that is going to be the top curve, which is x squared plus 2, minus the bottom curve, which is negative x dx. Be careful with your notation. And so then we can go ahead and work out that antiderivative, and this is what we get. We see that this combines and simplifies down to be the antiderivative from 0 to 1 of x squared plus x plus 2 dx, which is definitely an integral that you should be able to do without your calculator. And so we can run through the steps, and this is what we get. 17/6, once you get that all simplified down using FTC to go ahead and evaluate that definite integral. So these are pretty simple. You just are using 2 equations inside your integral instead of just the one. So let's look at one where we have intersecting functions. Okay. When we have those 2 functions never intersected, so that's why they had to give us a value of a and b that we could work through. Okay. So in this example, these 2 curves are going to intersect. So you'll notice they didn't give us values of a and b. So we might need to go ahead and figure out where those intersection points are. So if I look at these graphs, f of x I know is going to be a parabola because that's a quadratic function. I also notice that this is a perfect square. Now you can use any method you want to graph it, but knowing my transformations, that helps me out. I know that that is going to be the regular old parabola y equals x squared, just shifted to the left 1 unit. And so I know that that parabola is going to look like this. You can use an XY table to sketch your graph if you need to. If you're allowed to use your graphing calculator, then you can do it that way. So you just need to make sure that you can find the graph. So we have that. And then we need to graph the line y equals 2x plus 5. So that has a y-intercept of 5 and a slope of 2. So we can go ahead and plot those points. And I can tell because they were key points that I plotted on my parabola as well, I can tell where exactly these are going to intersect. We'd have to do a little bit of math if we weren't quite sure where they intersected. And so that's where being able to solve a system of equations is really, really important. We want to know where x squared plus 2x plus 1 equals 2x plus 5. You can use the intersect feature on your graphing calculator if this is a calculator active question, but this one is pretty straightforward to solve, and I would not be surprised if it was not a graphing calculator problem. So when we get this all to one side and set equal to 0, we get x squared minus 4 equals 0. And so our two solutions there are plus or minus 2. Those are the x values, and we can kind of confirm by looking at our graph that that seems about right. -2 and +2, so the region that we want the area of is going to be this one right here. Now, if we look at our picture for that interval of the graph, it looks like the line is the top curve, and it looks like the parabola is the bottom curve. So that's the order that we need to set it up in. So our integral is going to go from -2 to +2, and it's going to be the line 2x plus 5 minus the parabola x squared plus 2x plus 1. And make sure you take notice of my use of parentheses here, because we can't just subtract the x squared, we have to subtract that entire quadratic function. So remember that what that actually does is it's going to flip all of the signs in here. So that is really important. And so once you work that integral down, this would be one that you should be able to do without a calculator, but you can go ahead and work that and check your answer. We get 32/3 as the solution there. So that's sort of a basic introduction of finding the area between two curves.